Okay, so let's continue on with some of these things. I haven't finished off. I haven't finished off this row, so I haven't finished off that one here. Um, but I'm just gonna continue on with some of the numbers and just making sure that you have the right numbers at the end as well. So let's do. Um, let's do it this way. So these are the numbers that I got. And again, I haven't finished entirely everything. And then I'm not filling in the last row, although I've done it for a few, but I'm just not going to fill it in for now. So, in terms of the numerical, you have the equations there. So in terms of the numerical solution, you're given the frequency, or you're given the information of frequency, and if you're trying to solve for wavelength, then the number is, where is it? Oh, it's actually over there, 3.45 times 10 to the negative 7 meter. And if you're looking for the energy, then the energy is going to be 5.77 times 10 to the negative 19 joules. For the second row, you're given the information of energy, but you're not given the information about frequency or wavelength. And the answer numerically is that this one is 4.98 times 10 to the power of 14 second to negative 1. And the next one, the wavelength, is 6.023 times 10 to the negative 7 meter. And again, I'm not caring too much about sig figs and so on. Do you guys get the same-ish number? Yeah. Okay. And the last row, you are given the information of wavelength. So the frequency is 1.2 times 10 to positive 17 second to the negative 1, so inverse second. And then the energy is going to be 7.95 times 10 to the negative 17 joules. So those are some of the numerical solutions. I did not finish everything, but they're kind of repetitive from one to the other. But more or less, what you're doing is that you have this equation, and you get that number after plugging in all of this stuff. Right? So a lot of them is fairly plug and chug, although you need some algebraic rearrangement. Okay. Any questions before I keep moving on-ish? Yeah. Let's see. So why we're talking about light and photon in the first place? And more or less because light is the primary method of detection and characterization method for different molecules and compounds that one would synthesize in the laboratory, or if you're kind of interested in anything in particular. The atoms is so small, the only thing that's sufficiently small to be able to poke at it is light. And specifically, we're going through a process called the absorption or the emission spectroscopy. Majority of the time, we're going to be dealing with this one. Do you have to take the accompanying laboratory portion of this class at SMC at some point? Right? BL or something like that, yeah. So you're going to be doing a lot of absorption spectroscopy. Emission spectroscopy is also possible, but the machine is much more complicated. So usually it's not available for undergraduate laboratory, just because they're a bit more finicky, whereas absorption is a little bit easier to handle. But essentially, the concept is pretty straightforward. We have a variety of molecules with different energy levels. And specifically, we're talking about the energy of a particular electrons here. So these are electrons usually. And if we simply shine some particular energy of light, so that's E equals to hv is the energy of a photon. And if the energy of the photon is exactly equal to the difference between the energy difference between these two states, then you have an absorption. Whereas if you have an emission process, the process is simply reversed. That you have an electrons at a high energy level, and as it goes down to a lower one, it will emit a light or photons from that as well.
Do those correspond to orbitals, or are they
They do correspond to orbitals when we're talking about atoms, but most of the time we're talking about molecules. Then we get into, instead of atomic orbitals, we're going to call it molecular orbital. So at some point we're going to get into the molecular orbital theory as well, and just some of the basis of that. So that's just part of the reason why we're studying light and the photons of light, the energy of light, the energy of a photon, the wavelength, and so on. It's just because it's a characterization method, one of the most powerful characterization methods that we can get. So for all atom, there's a thing called the ground energy level. It simply means it's the lowest possible energy state of that particular atom. And that's essentially the slowest speed possible for the electron to spin, if you want to think about it, spinning around the nucleus. And it can't go any lower than that. That's called the ground energy level. And just symbolic-wise, usually we call this ground energy level as state of n equals to 1. So whenever you say n equals to 1, that usually tells you that's also the ground energy level. And these n is the quantum numbers and so on that you get. So essentially, you've probably heard about quantization of energy. It simply means that atoms have a quantized amount of energy levels and and so on, which we'll get into it. But we'll go to some of the simpler mathematics for now before we're going to that. Majority of the time, you'll see a graph that looks something like this, where if you're doing your own independent research, or if you're looking at the characterizations, things of particular molecules or atoms, these are the kind of scales that you'll see. And the reason, one of the reasons why I mentioned electron volt as the unit to be familiar with is because most of the tables are going to be written in terms of electron volt. The reason is pretty straightforward, because 1 electron volt is 10 to the negative 19 joule-ish. So it's much easier to write 1 EV rather than having to, or even in this case, negative 3.3 EV, rather than having to write like negative 6.7 times 10 to the negative 19. It's, once you have to write 10 to the negative 19 like 10 times, it gets pretty annoying. Hence, the electron volt is the preferred unit, or the more conventional unit to be used. Just like anything, some units are more preferred than others. So, if I were to have an energy transition from, where's my list? I'm going to follow from the stuff here. So if you have a transition from an n equals to 6 to an n equals to 5, so from this state to the one just right below it, do we have an absorption or emission process? N of 6 equals to n equals to 5. So if we have this energy transition, the electron is right here and it goes down in energy, then we have an emission. And the emission will then will produce a photon with an energy equals to the difference between these two states. So we know the energy of n equals to 6 is minus equals energy of n equals to 5. Okay. And just kind of as a good housekeeping, just put an absolute value in front of it. And if we look at from the graph, the energy of n equals to 6 is negative 0.38 electron volts minus the next one at the bottom is negative 0.54 electron volts. Then we get a difference of energy between the two of 0.12. No, hold on, that doesn't look right. Sorry, doing this on top of my head. 0.16, right? Yeah. So we know that the difference in the energy level between 6 and 5 is 0.6 electron volts, and the photon that is also being emitted from this particular transition will also have this amount of energy. It simply is a statement of conservation of energy. So we have an energy, we have our electron from a high energy level, it goes down to a lower energy level, and as it does so, it will release a particle of light with, so this is a photon, so the electrons goes down, and the energy of this photon is simply equals to the difference between the energy of these two states. So in this particular problem, the energy of the photon is 0.16 electron volt. And for convenience, I also asked you guys what is the wavelength of this particular photons in nanometer. And if you look back to the previous pages, you'll find a unit conversion table on the equation sheet that from the beginning, that 1240 is equal to the energy in electron volts times the wavelength in nanometer. So it's just a really convenient unit conversion factor. So rather than going from electron volt to joule to nanometer, we can simply use this particular value. So algebraically, if I want to solve for lambda, or the wavelength, this is going to be equals to 1240 divided by the energy, as long as the unit is in electron volts. So if we have a photon of 0.16 electron volts, the wavelength of that photon is equal to 1240 divided by 0.16. So it's just a really convenient conversion factor. This comes out to 7,750 nanometer. Right. So it's another equation. If there's too much equation and you'd rather use the other way, just convert it for joule. That's fine too. Yeah. Hold on. Yeah. So in this particular problem, we have an emission process from a higher energy, in this case n equals to 6 as the first portion of that problem, to go to n equals to 5. And if you look at n equals to 6, oops, sorry. The energy was negative 0.34, or sorry, 38 electron volt. And then the energy of n equals to 5 was, or is negative 0.54 electron volt. So the difference between the two is negative 0.16 electron volts. That's where the number comes from. I'm looking at it from the table that we have graphically. So yeah. So one of the applications that we can get is simply equals to the emissions and absorption spectrums, and so on. Again, the concept is pretty straightforward. If you want to know the energy of the photon that is being emitted or being absorbed, you simply have to look at the difference between the energy of those two states. Whatever that energy difference is going to be the energy of your photon, and whatever this value might be is going to be equals to hv if you're interested in frequency, or equals to hc over lambda if you're interested in the wavelength. So at this point, we're simply combining two different equations together. So let me kind of move away a little bit from the photons and so on. We'll do some more practice problem later on, but I do want to move on rather than doing a little bit more into more conceptual stuff, which is understanding the difference between wave and particle. Because I asked you guys to think about electrons and so on. This is rather choppy. And if you haven't taken physics, sometimes it becomes unclear in terms of what the difference between a wave and a particle is. And especially you want to know what is a wave and what is a particle before you understand wave-particle duality. And the best way to think about wave, so you know particles. Particles is basically any other object that you interact with every day. But the wave is essentially kind of this undulation. It's a repetitive. I should get a better distinction here. The best way to think about waves are basically oscillation. So all objects, in this particular case, lights and so on, they oscillate. Whether we're talking about sounds or light, they simply oscillate through space and time. But we don't care about that for now. But one of the main difference that you see between particles and a wave is a wave can undergo what's called the interference pattern. So a wave can undergo interference, and essentially the interference pattern is just like the picture that we have over here. So suppose that we have one wave, so it's a repetitive oscillation, and we lay it out with a second one that is exactly lines up with the first one. So where it goes up as well. So if we simply add these two together, we have a constructive interference. Simply means that the wave adds up. So the amplitude, so this is the initial amplitude, becomes larger because you add it up together. Right. So the amplitude gets bigger. We can also have a destructive interference where you have one wave and you overlap it with a second one that is exactly opposite in terms of its oscillation. It doesn't line up, essentially. And when you line it up together, you simply add it up. So if this is +1, this is -1, +1, -1, +1, -1. So when you add it up together, everything goes to 0, and this is called the destructive interference. And of course, you can have any scale between the two. You can have a tiny bit of interactions or a lot. So, so there's a gradient between this constructive and destructive interference. So this is what the property of a wave. So a wave can do things like these. So if you want to think about it, if you go to a big tunnel, sometimes there's a blind spot in your radio. That's more or less where there's a destructive interference because the sound is coming from two ends of the tunnel. The radio waves, is coming in from both sides of the tunnel, and as they collide in the middle, some part of it is going to be a disruptive interference pattern, so you don't hear anything on your radio. In some tunnel, even the 0-1. But you don't see the same behavior when you have a particle. That can't happen. That is, I can't line up these two things and it suddenly disappears. So a particle cannot undergo interference pattern. It can't do interference because that's what we see every day. It's just, if you have two things, two of the same object, collide them together. For one, they can't occupy the same space, and two, it's just not possible when we collide these two things and they simply disappears. So the best way to think about it is that the destructive interference could happen in a wave that cause it to completely disappear or completely add up. But it doesn't happen with the normal object that you see every day. So those are the difference between the wave and particle. But in chemistry, we operate in the assumptions that all objects, including atoms, electrons, neutrons, and so on, are both a particle and a wave, or a wave-particle duality. And the more normal interpretation, or the easiest interpretation of it is something like this. That is, if you have a particle, what we see as particles, what we touch and so on, is this little dot. But it actually have a wave property. So just like a droplet of water, there's a ripples across the surface of the water. But rather, when we're talking about actual three-dimensional particle, the ripple, so this is what we see as particle. And the wave property is that this particle is not exactly in space, but rather in one point in space, but rather it actually kind of ripples out like that. So that's kind of a more modern interpretation, I guess, of what is wave-particle duality. What we perceive as the positions of the molecule or particles and so on is simply the location where the amplitude is highest.
Location where the amplitude is the highest, that's where the particle is in that.
So in the classical definition.
Okay.
In the classical definition, the location of the highest amplitude is the location of the particle. But in fact, once we learned about quantum mechanics and so on, the position of the particle makes no sense because in fact, it spreads out throughout this wave. It's like all of these portion of the wave is the particle itself. It's simply a probability that there's some chance that there's the probability is here, some chances there, some chances there, but the highest probability corresponds to the position. Yeah, corresponds to the highest amplitude. And essentially, whenever we have like a moving object, like if you have an electron which is really, really tiny and it propagates to space, we have more or less the location of our electron is somewhat here. And as it propagates to space, it just kind of moves around like that. And if you kind of play around on the surface, it's like you've ever gone to a pool and you simply smack your hand on the surface, it kind of propagates. That's more or less about the same thing, pretty close, but not exactly the same. And that's the interpretation that we have. And of course, that's just when we're talking about a single particle. So what happens if we have, so this is the picture of a single particle, which is that one. And the important portion of here is that the amplitude is proportional to the probability of finding the electrons or the particle. The higher the amplitude, the higher probability of finding it. And what happens is that if you have multiple things lining up together, so suppose that I have like this computer, or I guess yourself, there's a bunch of atoms and molecules and a bunch of electrons and neutrons and so on in your body. So what happens is that we have a probability distribution that looks like this. So this is the probability of atom number 1, probability of atom number 2, probability of atom number 3, 4, 5, 6, and so on. Right? So if we simply undergo a constructive interference on each one of these things, you see that it looks more or less like that. So that's what we perceive as solid object. It's essentially these probability distribution overlapping, really constructive interference from one to the other to the other. It just looks like a flat surface, more or less. I'm trying to figure out where I'm trying to go with this. Oh, right. So let me actually put up that particular video because I like that one, so might as well put it up. Sorry, I'm trying to pull up the video that I want, which is this one here. Oh, what happened? I'm not sure why it's not showing up. Hold on. Oh, somehow it shows up. Okay. So when you have an object traveling to space, the picture is kind of like, is it actually going? No. So yeah. So if you have an object moving through space, I want you to notice that this one gets faster, a little bit faster, and it spins faster. That's your frequency and the wavelength and so on. As it goes slower, then you can see that for one, this oscillation, the wavelength gets bigger. It's the same thing again. If you have high energy particle, in which case it moves faster, the wavelength gets smaller. And again, as it moves faster, the frequency, so the oscillation, the speed in which oscillation, which is the frequency, gets faster, and the wavelength gets shorter. And what we perceive as a probability distribution is basically this thing here, which is the amplitude squared of the wave itself. And it just kind of oscillates back and forth. So that's kind of more or less the quantum mechanical pictures of what it's doing. This is, of course, is just one position in space, but the thing about quantum mechanics, and actually what makes mathematicians pretty happy, is that once you go to quantum mechanics, you have multiple dimensions opening up that, like, okay, this particle is simply moving from left to right, but the picture on the top is kind of circling about. That's because, essentially, you're opening up, the mathematics would only work if you opens up and create new space, like complex space. So it oscillates between imaginary numbers. Do you guys know what imaginary numbers are? The square roots of -1 is the formal definitions of imaginary numbers. But if you try to put square root of -1, it gives you error because it doesn't exist. Hence, it's called imaginary numbers because you can't put it in the calculator. But in the end of the day, it's actually real. It's not really imaginary. It's just complex. Hence, most of the time now, it's being called complex numbers rather than imaginary numbers, but they're the same thing. Anyway, it oscillates to different dimensions, which is beyond the scope of our class too. So yeah, so that's one. It's just what is a wave and what is a particle, and how can an object be both? Is essentially that picture there, or the same picture that we just saw before. What we perceive as the location of a particle is essentially the position where the amplitude is the highest. So it's a summary. And but the rule remains the same. That is, as the molecules or the particle moves faster, the frequency gets shorter, so it clumps up together. As the molecule gets slower, the frequency goes down, and the wavelength becomes bigger. So, no matter what it is. Now, so far, we've only been talking about the particle of light. But the thing is, light, or photons, is a really weird particle because, for one, it moves at the speed of light. It's a particle of light. It moves at 3 × 10⁸ meter per second, which is an incredibly fast speed. And the other thing, another quirky thing about photon, which is the particle of light, is that a photon have absolutely no mass. That's the definition of a photon. Or actually, one of the properties of a photon. It has no mass whatsoever. But that's obviously not the object that we interact with every day. So for one, I'm not moving at the speed of light. And for one, I'm certainly not massless. I'm quite heavy. So the equations, this is kind of annoying, but we have to have a new equation to describe these properties. That's a typo.
Yeah, because momentum is not mass divided by velocity.
Yes. Yes. So this is a typo. Sorry, typo again. So can you erase that equation, please? I'll update it online, but the whole thing, just kind of scratch it off. So there's a new equation to describe the wave property yeah, so this is the right equation. Yeah, that's the right equation. My point is that we're not photons, and we have mass, and we don't move at the speed of light. So the equation that describes the wavelength of anything else other than light is slightly different, actually pretty different, and it's called the de Broglie wavelength. And the de Broglie wavelength is lambda dB. Usually I put a little subscript here, but sometimes if you're doing any problems and so on, people don't put in the de Broglie or dB subscript there. So I just want you to know, if an object have a mass and it's not moving at the speed of light, so electrons have a mass, and for one, electron does not move at the speed of light. My cup does not move at the speed of light, and it has a mass. We need to use this particular equation for the wavelength. And the equation is h, which is our Planck's constant, the same. M here is the mass of the particle, and the mass of the particle have to have a unit of kilogram, and v is the velocity, or the speed and how fast the molecule is moving, and you want to keep the unit in terms of meter per second. So this is another wavelength equation, but this is called the de Broglie wavelength, and it's basically for any other object that's not light, because for one, they don't move at the speed of light, and all other objects have a mass. Now, the symbol, the conventional symbol, is annoyingly very similar. What I want you to notice is that this squiggly thing here, so if you see that, that is a symbol for frequency. So let me scratch it out. That's a symbol for frequency. And if you look at it, the V, and it just looks like a straight V, then this is for velocity. Yeah, it's a minute difference, but they do mean very different things. If you see the V with a little squiggle on the top, that's frequency. And if you see V without a squiggle, then that's velocity. I just want to highlight that just because the symbols are so similar from one to the other. And the other thing is that the energy for other particles that have a mass is going to be the energy is equal to 1/2 mv squared, because that's what you've learned from regular physics. Okay? So for one, the de Broglie wavelength, please do change it from your class planner, is h/mv. And the other one is that the energy of a particle is going to be that one, 1/2 mv squared. So let me kind of highlight the difference on the board here between the two. So if you have a photon, one has no mass, and two moves at the speed of light. The wavelength that you're interested in using is lambda is equals to c divided by frequency. Notice the squiggle on the top and on the bottom. And the energy in terms of wavelength, hc over lambda. Okay. But if we have any other object in the universe, everything else, more or less, have mass and moves kind of slowly. So the wavelength is going to be described as the de Broglie wavelength, hence the dB is h/mv, and the energy is the energy that you've learned in physics. It's just 1/2 mv squared. So the equations that you have to use in each one is a different one. It's actually kind of important that you distinguish between the two. So if I were to have a question, if I were to ask you, say, calculate the wavelength of an X-ray, which equations do you want to use? The photon one, so lambda is c over v. If I were to ask you what is calculate the wavelength of an electron, then you want to use lambda is equals to h/mv. Right? So it's just do make the distinction between the two. Just if it's not a photon, use the Broglie wavelength. Essentially the tips. But in any case, the picture remains the same. It spins and spreads out. The wavelength spreads out as it moves slower, and a contracted, or the frequency gets as the frequency goes up, the wavelength gets shorter and it moves faster. It remains the same in both, whenever we're talking either electrons or X-rays and so on. So yeah, we'll do some calculation later on. I kind of want to do some calculation here, but we'll skip it a bit and we'll go into any questions so far, actually, before I go on.
So to recap, because you have
Yeah.
questions here on the slow versus fast traveling wave.
Yeah.
Make sure I got it correct. The fast particle spins faster.
Yeah.
And the fast particle has a higher frequency.
Yep. Fast spin faster means it has high frequency.
And then it'll also have a shorter wavelength. The fast particle.
Yeah. Yep.
But
Yeah, it has to do with the probability. But the reason it spreads out is because the wavelength is bigger, so it spreads out more. Yeah. The one with the higher frequency is the faster one,
Yeah, I was just asking you.
and the shorter wavelength, the shorter the wavelength, the faster it moves, the more energy it has, right? And that's this one here is essentially answer to number 1, 2, and 3 as well. Alright, it's recording. The distinction is okay between de Broglie wavelengths and the other one, and photons. Yeah. So distinguishing between lights and pretty much any other particles. Light is kind of weird. What I do want to get to for now is there's a lot of experiments throughout the whole time that we study quantum mechanics, and in fact quantum mechanics didn't get formalized until about 1960s, so it's actually a pretty new science. I mean, it's been around for a while, but it really didn't get into essentially the formalism of what we've learned so far is really crystallized around 1960s. That's where Feynman is, most active, I suppose, which is a very famous scientist. But most of the time, we're just going to, for elementary chemistry at least, this new understanding about probability distributions, about quantum mechanics, about wave-particle duality, and why electrons or particles are both a wave and a particles, and so on, can be described with 3 different but very important experiments. I kind of want to get through a few of these, and certainly the double slit one, just because that's kind of one of the most important one. And then we'll go into the rest and what the contributions in each one as well. So the first one is the double slit experiment. So the double slit experiment tells you a particle, a photon, an experiment that will tell you whether a photon, which is light, is behaving as a particle or as a wave. And essentially, the best way to think about it is that we'll do a little bit of thought experiment. So suppose that I have a particle. So think of it as a baseball. And I try to throw a baseball through some tiny windows on that side of the wall. So that's my window. So if I keep throwing a ball or using a machine or something, what is the probability, or how would the ball falls on the other side of the wall, and what's the probability of that? Where the distribution in terms of where the ball that hits through here, how would it arrive on the other side? And essentially, most of the time, the ball would arrive right in the middle of the opening, right? So you have a high probability there. But sometimes it knocks over here and it kind of bounces around here a bit, or it can go the other way around. And what I'm trying to get to is that the probability, if you have something on the windows, opening on the windows, and you keep throwing stuff of it, and you hit, another side, then you'll see that the distributions in which it arrives on the other side of the board is going to be the highest right in front of the opening. And more or less it's going to look like that, right? It's the probability of the particle passing through is going to be highest right in the middle, but sometimes it bounces around a bit, so it's going to have some probability on the side, but not that much. And it decays pretty quickly. It's not up to scale, but yeah. So far so good? Yeah? So suppose that we have the same experiment, but now you have 2 openings. So instead of having just one window, one opening, you have 2 openings. And you keep throwing your balls onto the other side, you should see that the ball arrives. Well, on this side of opening, the probability is highest here, but the other side here is also highest. So what you should see is an overlap between these 2 things. Yeah. So what you see looks like that. Okay. Now, so if you have, so now we're talking about light particle. So if you have a light, so just like a regular light, and you put it through a small opening, what does the probability look like when it arrives to the other screen in front of the opening? Well, you've probably done that with, flashlight. And essentially you have a light source and you make sure that the opening is fairly small. And what you see from your flashlight is that the light is going to arrive more or less the same distribution like that. Right, so if you only have a single opening, this is what you'll see. So your light is shining, and you'll see that this one is bright. Right in front of the hole is bright, then it dissipates and gets darker and darker. But if you were to do this experiment, and instead of using a single slit, but instead you have two slits, what you'll see is something that looks like this. So this is what you'll see. So if you have a regular particle, so it's like a baseball, this is what you expect to see. You should see only two distribution, right across, and the intensity is highest right in front of the wall, in front of the opening. But instead, when you do this with light, what you see in the observation that looks like that. That is, it doesn't do it justice, but this is essentially, this is a bright spot, and then there's a dark spot. And then you have a bright spot, and another dark spot, and so on. And it's essentially make this oscillation. And let's kind of watch that a little bit while we're at it. I'm pretty sure this is the right video. Actually, let's watch it directly from this side here.
What is light?
What is light? What is light? That's a good question.
Out.
What is light?
Hold on.
Isn't it an element?
Light is brightness, I guess.
We have auras.
We all have auras.
Which are light?
Yes, they are. It lights up the room. It makes it